What if ancient civilizations possessed computational technology that rivaled modern computers? Devices that calculated astronomical events with stunning precision. Machines that predicted eclipses centuries in advance. Mechanisms built with gear systems so sophisticated they weren't matched until the 18th century. The official story says ancient people were primitive. They had basic tools, simple mathematics, no advanced technology. But artifacts recovered from the ocean floor tell a different story. Devices hidden in museum basements for decades. Mechanisms too complex to be explained by accepted timelines. Computational systems that challenge everything we've been taught about ancient capabilities. When these devices were first discovered, researchers couldn't explain them. The technology seemed impossible, so the artifacts were quietly stored away. The research suppressed, the implications buried. Why would evidence of ancient computational technology be hidden? Who benefits from maintaining the narrative that technological advancement is linear and recent? Today, we're examining 10 astronomical computers built before the birth of Christ. Each one demonstrates mathematical and engineering sophistication that shouldn't exist. Each one was downplayed, dismissed, or removed from mainstream discussion after initial discoveries. These aren't theories. These are physical artifacts, held in museums, studied by scientists, documented in reports that were later buried. Fair warning. This evidence contradicts standard historical narratives about technological progress. But the devices exist. The gears turn. The calculations work. The precision is measurable. 10 ancient computers. 10 examples of impossible technology. 10 cases where evidence was suppressed to protect comfortable narratives about human advancement. The pattern becomes undeniable when you see them all together. Number 1 is the device that started everything. Easter of 1901. Greek sponge divers working off the coast of Antikythera discover a shipwreck about 130 feet below the surface. A Roman cargo vessel, sunk around 70 to 60 BC. The divers recover statues, pottery, coins, standard archaeological finds. But one object doesn't fit. A corroded lump of bronze and wood, about the size of a shoebox. Covered in marine growth, it looks like junk. The archaeologists almost discard it. But when it dries out, it splits open. Inside are bronze gears, dozens of them, interlocking mechanisms, inscriptions in ancient Greek. This is no ordinary artifact. The object is sent to the National Archaeological Museum in Athens. It sits in storage for decades. Nobody knows what to make of it. The technology seems impossible for the ancient world. Then, in 1951, a British science historian examines it closely. Derek de Sola Price. He's from Yale University. He specializes in ancient scientific instruments. Price spends 20 years studying the mechanism. He uses X-rays to see inside the corroded bronze. He maps every gear, traces every inscription, calculates the mathematical ratios. What he discovers changes our understanding of ancient technology. The device is an astronomical computer, built around 100 BC. It contains at least 30 bronze gears. Some sources say closer to 40. The gears are cut with precision that requires advanced metalworking. The teeth are triangular, evenly spaced, machined to exact specifications. The mechanism calculates the positions of the sun and moon. It predicts eclipses. It tracks the Olympic Games cycle. It shows the phase of the moon. All mechanically, through gear ratios and differential gearing. Here's the problem. Differential gears weren't supposed to exist until the 16th century AD. That's 1600 years after this device was built. Price publishes his findings in Scientific American. The article creates shockwaves in the archaeological community. But the mainstream narrative doesn't change. The textbooks aren't rewritten. The device is acknowledged, but downplayed. Why? Because it contradicts the accepted timeline of technological development. If ancient Greeks had this level of mechanical sophistication, what else did they build? What other technology has been lost? The Antikythera mechanism is real. It's in a museum. Scientists have studied it extensively. Modern replicas have been built, and they work perfectly. but the implications remain suppressed. The device is treated as an anomaly, an exception, a one-time achievement that doesn't represent broader ancient capabilities. The evidence says otherwise. As you're about to see, this wasn't the only ancient computer. Number 2 was discovered in Iraq. 1929. German archaeologists excavate ancient Babylon. They uncover thousands of clay tablets, mathematical texts, astronomical records, cuneiform inscriptions covering centuries of observations. Among these tablets are something extraordinary: computational tables, pre-calculated values for complex astronomical predictions. The Babylonians weren't just observing the sky, they were computing. Dr. Otto Neugebauer leads the analysis. He's a mathematician and historian of science. He deciphers the cuneiform mathematical notation. What he finds astonishes him. The tablets contain ephemerides, tables showing planetary positions for specific dates, predictions of lunar eclipses, calculations of planetary movements, all computed using sophisticated mathematical algorithms. The Babylonians developed a system for predicting lunar eclipses with remarkable accuracy. They tracked the Saros cycle, an 18-year period after which eclipses repeat. But they went further. They calculated variations, adjustments for the elliptical orbit of the moon. Neugebauer analyzes the mathematics. The Babylonians used arithmetic sequences. They understood numerical patterns. They developed algorithms that could generate predictions for centuries into the future. These aren't simple observations. This is computational astronomy, mathematical modeling of celestial mechanics, done without telescopes, without calculators, without modern mathematical notation. The tablets date to the Seleucid period, around 300 to 100 BC. But the mathematical systems they use are older, much older. Some methods trace back to the 7th century BC or earlier. Neugebauer publishes his research, academic papers, detailed translations, mathematical analysis. The evidence is irrefutable. The Babylonians had computational astronomy centuries before anyone thought possible. But the discovery doesn't change mainstream narratives. The tablets are acknowledged in specialist circles, but they're not integrated into broader understanding of ancient technology. They're treated as isolated achievements, mathematical curiosities. The reason is clear. These tablets prove ancient civilizations had systematic computational methods. They could predict celestial events with precision. They had mathematical sophistication that challenges linear models of technological progress. The tablets exist in museums today: the British Museum, the Louvre, universities around the world. The mathematics has been verified. The predictions tested against astronomical data. They work. But the implications remain compartmentalized, discussed in academic papers, not taught in mainstream education, not acknowledged in popular understanding of ancient capabilities. The pattern continues. Evidence exists. It's verified. Then, it's quietly minimized. Number 3 takes us to ancient China, the year 104 BC, the Han Dynasty. Chinese astronomers build a device called the armillary sphere, a mechanical model of the celestial sphere, bronze rings representing the celestial equator, the ecliptic, the meridian. But this isn't just a model. It's a computational device. The sphere is mounted on a rotating axis, driven by water power. A constant drip mechanism turns the sphere at the exact rate of Earth's rotation, one complete revolution every 24 hours. The device tracks stellar positions, planetary movements, the sun's path through the zodiac, all mechanically, all automated. But here's what makes this extraordinary. The gearing system required to convert water drip into precise rotation demands advanced mechanical engineering, gear ratios, escapement mechanisms, precision metalwork. Zhang Heng improves the design in 132 AD. He adds a seismoscope, an earthquake detector. The device uses pendulum mechanisms to detect ground vibrations. Directional indicators show which direction the earthquake originated. The armillary sphere includes computational elements, gear systems that calculate astronomical positions, mechanical automation that requires understanding of ratios and timekeeping. engineering that matches European clockwork built 1500 years later. Joseph Needham documents this in his research on Chinese science. He's a British biochemist who becomes fascinated with Chinese technological history. He spends decades studying ancient Chinese inventions. Needham's findings are published in the 1950s and 60s. His work shows Chinese astronomical instruments achieved mechanical sophistication centuries before European equivalents. The armillary sphere used differential gearing, complex gear trains, automated timekeeping mechanisms, all before the birth of Christ or shortly after. But Needham's research remains marginalized. It's acknowledged in specialist literature, but it doesn't change mainstream narratives about technological development. The story still goes. Meaningful mechanical technology begins in medieval Europe. Eastern achievements are footnotes. This framing serves a purpose. It maintains Western-centric models of innovation. It supports the narrative that technological advancement is recent and linear. The evidence contradicts this completely. Chinese astronomical computers were operating while Europe was in the Dark Ages. The mechanical sophistication was extraordinary. The computational accuracy was remarkable. Replicas have been built. They work. The astronomical calculations are verified. The mechanical systems function as designed, but the implications are ignored. If ancient China had this level of mechanical computing, what else did they develop? What knowledge has been lost? What technologies existed that we've forgotten? The pattern repeats. Physical evidence exists. It's studied. Then it's quietly filed away. The narrative remains unchanged. Number 4 was found in Egypt, early 20th century. Archaeologists excavate ancient Egyptian temples. They find astronomical texts, star charts, tables showing stellar positions, calculations of seasonal changes. The texts describe something called the merket, an astronomical instrument used to align pyramids, to track stars, to measure time at night. The merket is simple in design: a wooden rod, a plumb line, a sighting tool made from palm ribs, but its application demonstrates computational sophistication. Egyptian astronomers used the merket to establish true north. They sighted on stars, tracked their positions, calculated celestial mechanics, all without telescopes or modern instruments. The Great Pyramid at Giza aligns to true north within 1/15 of a degree. That's extraordinary precision. Achieving this requires astronomical observations, mathematical calculations, understanding of stellar mechanics. Dr. Kate Spence from Cambridge University publishes research on pyramid alignment. She shows the Egyptians used simultaneous observations of two stars, Kochab and Mizar. By tracking when these stars aligned vertically, they could determine true north. But this method requires computational astronomy, understanding precession, calculating stellar positions for specific dates, predicting alignment events. The pyramids were built around 2500 BC. The astronomical knowledge required predates classical Greek astronomy by 2,000 years. Spence's research is published in Nature, a prestigious scientific journal. The evidence is solid. The mathematics work. The astronomical methods are verified. But the discovery doesn't change mainstream narratives. The pyramids are still described as monuments built with simple tools. The sophisticated astronomical computation is downplayed, mentioned briefly, not emphasized. Why? Because it contradicts the narrative of primitive ancient cultures. If Egyptians had computational astronomy in 2500 BC, the timeline of scientific development needs revision. The merket survives in museum collections. Multiple examples exist. The astronomical texts are translated. The mathematical methods are documented. Modern astronomers have verified the techniques. They work. The precision is achievable using the methods described. The computational approach is sound, but the implications remain suppressed. Egyptian computational astronomy is treated as an isolated achievement, not evidence of broader technological sophistication. The pattern is clear. When ancient technology surpasses expectations, it gets acknowledged in specialist literature, but the broader narrative remains unchanged. The comfortable story persists. Ancient people were primitive. Real technology is recent. The evidence says otherwise. The devices exist. The mathematics work. The precision is measurable. Number 5 takes us to the Maya civilization, deep in the jungles of Central America. Ancient observatories, stone structures aligned to astronomical events, windows positioned to track Venus, the sun, the moon, specific stars. The Dresden Codex survives the Spanish conquest, one of only 4 Maya books not destroyed. It contains astronomical tables, eclipse predictions, Venus cycle calculations, computational astronomy recorded on bark paper. The Venus table is extraordinary. It tracks the synodic period of Venus with stunning accuracy. The Maya calculated Venus returns to the same position relative to Earth every 584 days. Modern astronomy measures this at 583.92 days. The Maya were off by 0.08 days. Over a 1,000-year tracking period, the error is negligible. But calculating this requires sustained astronomical observation, mathematical modeling, computational methods to track cycles and predict future positions. The Dresden Codex dates to the 11th or 12th century AD, but the astronomical knowledge it contains is much older. The observations span centuries, the computational methods developed over generations. Dr. John Teeple analyzes the Venus table in the 1930s. He's an American chemical engineer who becomes fascinated with Maya astronomy. He decodes the mathematical basis of their calendar systems. Teeple shows the Maya used correction factors. They adjusted their calculations to account for fractional days. They understood their initial values weren't perfect, so they built in computational adjustments. This is sophisticated astronomical computing, algorithmic thinking, error correction, iterative refinement of mathematical models. The Maya also tracked lunar cycles, predicted eclipses, calculated the synodic periods of Mars and Jupiter, all without telescopes, without modern mathematics, without calculators. How did they achieve this precision? Sustained observation, mathematical sophistication, computational systems that allowed predictions spanning centuries. Teeple publishes his research, academic papers, mathematical analysis. The evidence is documented, the calculations verified. But the mainstream narrative doesn't change. The Maya are still described as primitive. Their astronomical achievements are mentioned but downplayed, treated as lucky guesses or simple pattern recognition. This framing is intentional. Acknowledging Maya computational astronomy means acknowledging sophisticated indigenous science, mathematical systems that rivaled European astronomy of the same period. The Dresden Codex exists. It's in a library in Germany. Scholars have studied it extensively. The astronomical tables are translated, the mathematics analyzed, the predictions tested. They work. The Venus cycle is accurate. The eclipse predictions are verified. The computational methods are sound, but the implications are ignored. Maya astronomical computing is treated as an anomaly, not evidence of systematic scientific knowledge, not recognition of computational sophistication. The pattern continues. Evidence exists. It's real. It's verified. Then it's minimized. Number 6 was discovered in India. Ancient Sanskrit texts describe astronomical instruments, computational methods, mathematical algorithms for predicting celestial events. The Surya Siddhanta is one such text, dating to the 4th or 5th century AD, but containing astronomical knowledge that's much older. The text describes planetary motions, orbital periods, eclipse predictions, the circumference of Earth, all computed with remarkable accuracy. The Surya Siddhanta gives Earth's diameter as 7,920 miles. Modern measurement is 7,926 miles. The ancient calculation is off by 0.08%. How did ancient Indian astronomers achieve this precision? Computational astronomy, mathematical modeling, systematic observations refined over centuries. The text describes yantras, astronomical instruments, mechanical devices for computing planetary positions, gear-driven models of celestial mechanics. Aryabhata, writing in 499 AD, describes computational methods for astronomy. He gives the sign table, explains planetary periods, describes Earth's rotation, all mathematically computed. Aryabhata's calculations for planetary orbital periods match modern values within small margins. His value for the sidereal year is 365.2586 days. Modern measurement is 365.2563 days. The difference is 0.0023 days. This level of precision requires sophisticated computational astronomy, mathematical algorithms, systematic error correction, computational devices or methods that allowed complex calculations. Dr. B. V. Subbarayappa studies ancient Indian astronomy. He documents the mathematical sophistication, the computational methods, the astronomical instruments described in texts. His research shows ancient Indian astronomers had systematic computational approaches. They understood trigonometry, used algorithms for astronomical calculations, built instruments that mechanized these computations. But this research remains compartmentalized, discussed in specialist literature on Indian science history, not integrated into mainstream narratives about technological development. Why? Because acknowledging advanced computational astronomy in ancient India challenges Western-centric models of scientific progress. The story becomes more complex. Multiple centers of innovation, different paths to technological sophistication. The texts exist. The mathematics has been analyzed. The astronomical values verified against modern measurements. The precision is undeniable. Replicas of ancient Indian astronomical instruments have been built. They work. The computational methods are sound. The predictions are accurate, but the implications remain suppressed. Ancient Indian computational astronomy is treated as a separate tradition, not evidence of widespread ancient technological capability, not recognition that multiple civilizations achieved computational sophistication. The pattern persists. Evidence is documented, verified, then compartmentalized. The broader narrative, unchanged. Number 7 brings us to ancient Persia, the Islamic Golden Age, 9th to 13th century AD. But the astronomical knowledge comes from earlier Persian traditions, pre-Islamic computational astronomy. The Zij astronomical tables are extraordinary. Massive compilations of astronomical data, planetary positions, eclipse predictions, star catalogs, all computed with precision. Al-Khwarizmi publishes his Zij in 820 AD, but he's working from Persian sources, Sasanian astronomical tables, knowledge dating back centuries. The Zij contains computational algorithms, step-by-step methods for astronomical calculations. These aren't just observation records. They're computational procedures, algorithms. Al-Khwarizmi's work gives us the word algorithm. His mathematical methods are systematic, computational, designed to produce accurate astronomical predictions. The astronomical instruments are equally sophisticated. The astrolabe, a portable computational device, bronze discs, rotating components, engraved scales. The astrolabe calculates stellar positions, time, latitude, astronomical events, all mechanically. The device uses stereographic projection, a mathematical mapping of the celestial sphere onto a flat plane. This requires sophisticated geometry, understanding of spherical coordinates, mathematical sophistication. Astrolabes date back to ancient Greece, possibly earlier, but they're refined and mass-produced in the Islamic world. Hundreds survive in museum collections. These devices are astronomical computers, mechanical calculators for celestial navigation and timekeeping. The mathematical basis is complex. The mechanical execution requires precision metalwork. Dr. David King studies Islamic astronomical instruments. He documents thousands of artifacts, analyzes their mathematical basis, shows their computational sophistication. King's research reveals the astrolabe wasn't just a scientific instrument. It was a computational device available to navigators, astronomers, even educated merchants. Portable computing power for astronomical calculations. But this computational technology is rarely emphasized in mainstream history. The Islamic Golden Age is acknowledged, but the mechanical computational devices are treated as curiosities, not as evidence of widespread computational technology in the medieval period. The reason is clear. Acknowledging sophisticated computational devices in medieval Islam contradicts narratives about European technological supremacy. The timeline becomes complicated. The geography of innovation broadens. Astrolabes exist in museums worldwide, hundreds of examples. The mathematics has been analyzed. Modern replicas work perfectly. The computational capacity is verified. The Zij tables are translated. The algorithms documented. The astronomical accuracy confirmed. These were systematic computational systems, mathematical astronomy at a sophisticated level. But the implications remain minimized. Islamic computational astronomy is acknowledged in specialist literature, not emphasized in popular understanding, not integrated into broader narratives about technological capability. The pattern continues. Evidence accumulates. Devices exist. Mathematics is verified. Then the significance is downplayed. Number 8 was discovered in England. Stonehenge. Built around 3000 to 2000 BC. Massive stones arranged in specific patterns, aligned to astronomical events: summer solstice sunrise, winter solstice sunset, lunar standstills. For decades, Stonehenge was treated as a primitive monument. Ceremonial stones. No real purpose. Ancient people marking seasons through simple observation. Then in the 1960s, Gerald Hawkins changes everything. He's an astronomer. He analyzes Stonehenge using computer modeling, maps every stone position, calculates sightlines, tests astronomical alignments. What he discovers is extraordinary. Stonehenge is an astronomical computer. The stone positions mark lunar and solar events with precision. The monument tracks eclipse cycles, predicts celestial events. All mechanically encoded in stone placement. Hawkins publishes his findings in Nature. The article is titled, "Stonehenge Decoded." He shows the monument aligns to 56 significant astronomical events. The probability of this being coincidence is essentially zero. The 56 Aubrey holes, a ring of pits around the monument. Hawkins proposes they tracked lunar cycles. Moving markers around the circle predicted eclipses. A mechanical computational system built in stone. The builders of Stonehenge had sophisticated astronomical knowledge. They understood lunar standstills, solar cycles, eclipse prediction. They encoded this knowledge in permanent architecture. But this requires computational astronomy, mathematical understanding of celestial mechanics, the ability to predict events decades in advance, all in the Stone Age. Hawkins's research is controversial. Mainstream archaeologists resist. They prefer the ceremonial monument explanation. The computational interpretation is too sophisticated, too advanced for Neolithic people. But subsequent research confirms Hawkins's basic findings. The alignments are real. The astronomical significance is undeniable. Stonehenge incorporates computational astronomical knowledge. Dr. Alexander Thom conducts extensive surveys. He measures stone circles across Britain. He finds consistent astronomical alignments, standardized units of measurement, mathematical relationships. Thom proposes Neolithic people had systematic astronomical knowledge. They built computational monuments across the landscape, stone circles as astronomical calculators. His research is published, documented, verified by other researchers. The astronomical alignments are real. The mathematical relationships exist, but mainstream narratives resist. Stonehenge is still primarily described as a ceremonial monument. The computational aspects are mentioned but downplayed, treated as secondary to spiritual purposes. This framing serves a purpose. Acknowledging Stonehenge as an astronomical computer means acknowledging Neolithic computational sophistication, mathematical knowledge, scientific thinking. This contradicts narratives about primitive Stone Age cultures. The monument stands. The alignments are measurable. The astronomical significance is documented. Modern researchers have verified the computational capacity, but the implications remain suppressed. Stonehenge, as an astronomical computer, challenges too many assumptions, so the evidence is acknowledged but minimized, the narrative unchanged. Number 9 takes us to ancient Rome. The Pantheon in Rome. Built around 125 AD, Emperor Hadrian commissions the construction. The dome is extraordinary, 43 meters in diameter, perfect hemisphere, unreinforced concrete. The oculus at the top allows sunlight to enter. But the Pantheon is more than architecture. It's an astronomical instrument. The oculus tracks the sun's movement. The light beam sweeps across the interior, marking time, tracking seasons, computing celestial events. The building is oriented precisely. The entrance faces north. The meridian line runs through the center. The interior space functions as a solar calendar. On the equinoxes, the sunbeam strikes specific points. At noon on April 21st, the founding date of Rome, the light illuminates the entrance. This isn't coincidence. This is computational design. Dr. Robert Hanna studies the Pantheon's astronomical functions. He's a classics professor from New Zealand. He analyzes the building's geometry, the proportions, the alignments. Hanna shows the Pantheon was designed as a cosmic calculator. The dome represents the celestial sphere. The oculus represents the sun. The movement of light through the interior computes astronomical time. The building's proportions are mathematically precise. The diameter equals the height. Perfect geometric relationships throughout. The coffers in the ceiling reduce weight while maintaining structural integrity. Engineering that wasn't matched for over 1,000 years. But the astronomical computational function is rarely emphasized. The Pantheon is described as an architectural marvel, a temple. The computational aspects are mentioned in specialist literature, not emphasized in popular understanding. Why? Because acknowledging the Pantheon as an astronomical computer means acknowledging Roman computational sophistication, scientific thinking integrated with architecture, mathematical astronomy encoded in permanent structures. The building stands in Rome today. The astronomical alignments can be verified. The solar computations work. The geometric precision is measurable. Researchers have documented the computational functions, the seasonal markers, the celestial tracking. The building computes astronomical time through its geometric design, but these findings remain compartmentalized. The Pantheon is famous for its dome, its architecture, its preservation, not for its computational astronomical functions. The pattern continues. Evidence exists. It's documented. Physical structures prove ancient computational capability. Then the significance is minimized. The narrative focuses on other aspects. The computational sophistication downplayed. The Pantheon was an astronomical computer built in concrete and stone, a permanent computational device, tracking celestial events, marking sacred times, computing the cosmos. But acknowledging this fully would require rethinking Roman scientific capabilities, recognizing systematic astronomical knowledge, computational thinking integrated with monumental architecture. So the evidence is noted, then filed away. The building remains, the computations work, the implications ignored. Number 10 brings us to ancient Mesopotamia. The Mole. Apen tablets. Cuneiform astronomical texts, dating to around 1000 BC, but containing knowledge that's much older, possibly from 2000 BC or earlier. These tablets are astronomical computers in written form, lists of stars, constellations, planetary movements, rising and setting times, all computed, all systematic. The tablets describe computational methods, algorithms for predicting celestial events, mathematical procedures for astronomical calculations. This isn't just observation, this is systematic computation. The Mu Apen system tracks the heliacal rising of stars, when stars first become visible before sunrise. This was used for calendrical purposes, agricultural timing, religious festivals. But computing heliacal risings requires understanding stellar positions, accounting for precession, calculating visibility conditions. Mathematical astronomy The tablets describe the zodiac, 12 constellations along the ecliptic, the path of the sun through the stars. The Babylonians mapped this, divided it into systematic segments, created a coordinate system for tracking planetary positions. This is computational astronomy, a reference frame, mathematical coordinates, systematic tracking of celestial objects. Dr. Hermann Hunger translates and analyzes the Mul-Appen tablets. He's an Assyriologist. He shows the tablets contain sophisticated astronomical knowledge, computational methods, systematic procedures. The tablets describe planetary periods. Venus returns to the same position every 8 years. This is the Venus pentagram, a pattern known to Babylonian astronomers, computed and verified over centuries of observation. The tablets give the length of the year, seasonal divisions, shadow lengths for timekeeping, all computed, all mathematical. This computational astronomy dates to at least 1000 BC. The knowledge is systematic. The methods are algorithmic. The predictions are verifiable. But these tablets are rarely emphasized in popular understanding of ancient technology. They're known to specialists, Assyriologists, historians of science, not integrated into mainstream narratives. Why? Because acknowledging Mesopotamian computational astronomy from 1000 BC or earlier means acknowledging systematic scientific thinking, mathematical sophistication, computational methods, all in the Bronze Age. This challenges narratives about scientific development. The story becomes more complex. Multiple ancient civilizations developed computational astronomy, independent traditions, different methods, all achieving sophisticated results. The tablets exist. The British Museum holds them. The cuneiform has been translated. The astronomical content analyzed. The computational methods documented. Modern astronomers have verified the predictions. The planetary periods are accurate. The stellar observations are precise. The computational algorithms work. But the implications remain compartmentalized. Mesopotamian computational astronomy is acknowledged in specialist literature, not emphasized in popular history, not integrated into broader understanding of ancient technological capability. The pattern completes. 10 ancient astronomical computers. 10 examples of sophisticated computational technology. 10 cases where evidence exists but implications are suppressed. 10 computational devices. 10 examples of astronomical sophistication. 10 cases where ancient technology exceeded expectations and was quietly downplayed. The antikythera mechanism with its differential gears. Babylonian astronomical algorithms. Chinese armillary spheres with automated mechanisms. Egyptian computational astronomy aligning pyramids. Maya Venus calculations, accurate to fractions of a day. Every case demonstrates the same pattern. Ancient civilizations developed computational astronomy, mathematical sophistication, mechanical devices, systematic scientific methods, knowledge that supposedly didn't exist, technology that contradicts linear models of progress, computational capability that challenges accepted timelines. When these devices were discovered, mainstream narratives should have changed. Textbooks rewritten, historical models revised, recognition that ancient people were far more capable than previously thought. But that didn't happen. The devices are acknowledged, studied in specialist circles, then compartmentalized, treated as anomalies, exceptions, isolated achievements. Why? Because full acknowledgement would require fundamental revision of how we understand technological development. The comfortable narrative says real science begins with Greeks. Real technology emerges in Europe. Progress is linear and recent. The evidence contradicts this completely. Multiple ancient civilizations independently developed computational astronomy, mechanical computers, mathematical algorithms, scientific methods. This knowledge was real. The devices exist in museums. The mathematics has been verified. The astronomical predictions work. The mechanical systems function. But the implications threaten established models. Academic careers built on outdated assumptions. Educational systems teaching simplified narratives. industries benefiting from the myth of modern superiority. So the evidence is acknowledged but minimized. The devices are real but exceptional. The knowledge is documented but compartmentalized. 10 ancient computers prove computational technology existed before Christ. Sophisticated mathematics, mechanical engineering, scientific thinking, all developed independently across multiple civilizations. These aren't theories. These are physical artifacts, mathematical texts, astronomical instruments, mechanical devices, all documented, all verified, all real. The question isn't whether ancient people had computational technology. The evidence proves they did. The question is why this evidence remains suppressed in mainstream understanding, why the implications are avoided, why the narrative hasn't changed. The answer lies in who benefits from maintaining simplified historical models, who profits from the myth that real technology is recent and Western. What assumptions would need to be abandoned if we fully acknowledged ancient computational sophistication? The devices remain. The mathematics work. The astronomical predictions are accurate. The mechanical systems function. The evidence is undeniable. What you believe about ancient technological capability is your choice. But the artifacts exist. The computations are verified. The pattern is clear. They count on people not looking closely, not questioning comfortable narratives, not examining the evidence in museum basements and specialist publications. But the ancient computers are waiting. The gears still turn. The mathematics still work. The astronomical predictions still compute. 10 devices. 10 examples of forbidden knowledge. 10 cases where truth contradicts accepted history. The evidence has been presented. The pattern revealed. The computational sophistication documented. Stay curious about what else has been quietly filed away. Stay skeptical of simplified narratives. Stay focused on physical evidence over comfortable stories. The ancient computers prove one thing conclusively. Our ancestors were far more capable than we've been taught. The technology existed. The knowledge was real. The computational sophistication undeniable.